Oh, hey. Aha! Science.
1, 2, 3. So, what you doing? Oh, I'm counting rocks on Mars. Oh, that's cool. I'm counting rocks on Mars in order to geomorphically map out glacial features on Mars in order to understand changing climate on Mars and thus identify possible climates in which life could have been present on Mars and possibly find evidence for life on Mars. So don't distract me or else I'll lose count. 1, 2.
Oh, 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 oh.
3, 4. You made me lose count. Oh, sorry about that. Well, let me tell you about it anyway. Go. I'm always down to learn. Let's talk about Mars, glaciers, possible signs of life, climate change. Let's do it.
So you know that climate change is happening here on Earth, but did you know that climate change is also occurring on other planets, including Mars? This is all because due to its orbital parameters, where it's located in relation to the sun, what its axial tilt looks like. This can all affect Mars's climate. And so, if in the past Mars had a warmer, wetter climate due to its position in the sun, its axial tilt, and other orbital parameters, then there might have been a higher chance for life to be present there on Mars. But the thing is, how can we even begin to look at climate change on Mars when it's over 100 million miles away and no human has ever stepped foot on it? And that is where we can look at Mars's glaciers. They record the footprint. They record the history of Mars's climate. And up until now, it has been a big question about whether or not Mars has had one very long extended ice age or if it had multiple short periodic ice ages. And there's now evidence suggesting that we have those short episodes. But in order to understand the amazing stories that Mars's glaciers can tell us, first we need to understand a bit about glaciers. So let's dive into the whiteboard.
Now here we have our glacier. A glacier is essentially a river of ice and rock that's flowing down here from the mountains. From where all the snow has fallen from the mountains, it slides down into this giant river of ice and rock. And you see here, just like a river, along the edges, you get slower flow, and thus rocks will be deposited. Rocks will be left behind here on the edges and here in the middle where the ice isn't flowing as fast. These are called moraines. So you have your lateral moraines and your medial moraines. At the end, at the end of the glacier, you get a bunch of deposition of rocks, and this is called a terminal moraine. And so the current terminal moraine for this glacier right here is right here. But you can see that in the past, when the glacier was bigger, the terminal moraine was here, and even later in the past, the glacier was here. And so you have the terminal moraine here, the rocks being deposited here. And so by looking at these patterns of rock deposition, the locations of these moraines, where all the rocks that was in the ice gets deposited, either due to the slow-moving ice or when the glacier melts, the rocks just fall down into place. By looking at these moraines, we can look at the past climatic history of glaciers. Now, this is an Earth glacier, and similar principles apply to glaciers on Mars. So, let's look at these Mars glaciers.
So here we go. We have beautiful Mars here. You can see it's red because of all that iron. You can see all these craters everywhere. But let's look at that snowy good white stuff. So we go up here to the polar caps. Here at the North Pole, you see the snow. Here in the South Pole, you see the snow. Well, we're not talking about that snow. No, we're not talking about those glaciers. We are talking about glaciers at lower latitudes. Let me add these grid lines. You see, because these are glaciers that occur on Mars between 30 and 60 degrees latitude. So within this band here. And so you can see there isn't any snow. There isn't any ice. What's going on? Well, the glaciers are hiding beneath the surface. They are beneath the rocks. They are beneath the soil. They are covered up. So that's why you can't see them, but those are the glaciers that we're talking about.
Yeah, you heard that right. Those glaciers are undercover.
You see, it's important that the glaciers on Mars are, especially in those lower latitudes, are covered in rocks and debris, because if the ice was just exposed on the surface, the sun would melt the glaciers. And so the rocks and debris act as a shield, protecting the ice from the sun. Just like closing your refrigerator door. You don't leave your refrigerator door open or else your stuff will melt. You gotta cover it with the door. You gotta cover glaciers on Mars with rocks or else they melt. And I'm looking at those moraine-esque rocks. Remember where the rocks are deposited? That's what tells us our climatic story. It's a climatic story and a climatic story. And what's really great about having this Mars glacial data is that we can compare the glacial climate data to the Mars's planetary orbital data. You see, climate has a lot to do with a planet's position relative to the sun and the planet's orbital tilt and other parameters that depend on this orbit. And the thing about Mars is that we have really good models that go back about 20 million years, but Mars's axial tilt is super chaotic, and thus it makes it hard to project past 20 million years. But with this glacial data, we can ground truths on these models and hopefully get more insight into Mars's orbital parameters past 20 million years ago. Mars's axial tilt. More chaotic than me at the club after downing a gallon of Kool-Aid with added pixie sticks. Now, when planetary geologists were looking at these glaciers on Mars through satellite imagery, there was a lot of big questions whether these glaciers had formed over one continuous ice age. Just due to Mars's coldness, did this ice form continually over the past several 100 million years, or did the ice form in small bursts? Was it every once in a while, every several thousand years, would ice accumulate and then melt, and then accumulate and then melt? It was hard to tell from the images alone which model that was. And that's a huge question. Was Mars's climate sticking around in this ice age for several 100 million years? Or did it have lots of small little ice ages lasting only several thousand years? That's an important question, understanding Mars's history. That's an important question, understanding possible life history on Mars. That's an important question, understanding where we can find ice. That's an important question, understand what data we can get from Mars. We need to know when this ice formed, how often, and the mechanisms. To discuss these two theories, let's go back to the whiteboard. So if ice has been accumulating on Mars for the past several 100 million years, then we would expect a model similar to this. Well, we could hypothesize at least that we would have rocks accumulating here in the mountains. So we'd have these big rocks accumulating in the glacier
in the mountains. And those rocks, as the glacier flowed downwards, would be carried downwards. And so they would be continuing downward, but as they go downward, they're eroding, they're crashing into other rocks, and slow they get smaller, and they get smaller, and they get smaller, until they get to our terminal moraine here at the end. So you can see that the rocks, they're evenly distributed about the glacier, but they are bigger here in the mountains, and they get smaller as they go down into the valley. And this would continue and continue throughout time as we have this stable ice going down, and we would just have this even distribution of rocks across the glacier. And that's what we would expect to see on Mars's surface, an even distribution of rocks. Now, this is what it would look like if Mars had punctuated ice-forming events. So this is what Mars looks like right now. Right now, where Mars is not actively forming ice in these lower latitudes where we have these debris-covered glaciers. It's an interglacial. It is not actively making ice. And so what we are getting is our good old classic erosion. So rocks, they're falling down the mountain and they're gathering here in the mountains. This is the active process that's occurring on Mars today. We are getting these rocks here in the mountains. Now, when the orbital parameters are right and we get an ice age, then ice will form and we'll get our glacier forming. And what will happen is these rocks will be carried down by the ice through the glacier. And then these rocks, they will travel down until the ice is melted away, they reach the end, or the ice melts, it sublimates. It goes right, it disappears, leaving that is a crappy eraser, but that's okay. Leaving the rocks in place. And so we see that those rocks are stuck in place because the ice is melted, leaving them in these bands. So let's go through that again if we can. We have no ice, so the rocks, they're accumulating here in the mountains, and then ice forms, causing our glacier. The rocks get carried downwards until the ice stops. If the ice is gone, and so we get a band of rocks. And you can imagine if this continues several times, we'll get a band of rocks here. We might get a band of rocks here because the glacier got a little bit bigger, a little bit larger. It was able to last longer. Maybe we'll get a band of rocks here. It was a really quick, short glacial period. We'll get a band of rocks here, and we'll see these bands of rocks. Areas where there aren't a lot of rocks, areas where there are a lot of rocks, banding. Unlike that continuous model where the rocks were evenly distributed throughout the glacier.
So in order to test these models, an army of researchers spent a long time looking at super high resolution NASA imagery of Mars, such that they could zoom in and look at individual boulders on these debris covered glaciers. They could look at, basically super high resolution. They were seeing individual boulder rocks and they were counting them. Mapping out their positions on the glacier. And guess what they found? They found that banded pattern. The rocks were not evenly distributed across the glacier. No, they occurred in bands, indicating that there are multiple glacial, interglacial transitions, periods of ice formation and periods of ice loss over these 100 millions of years. And what's also interesting is that they ran some statistics to try to figure out exactly how many of these transitions there were, and they have got about 5 or 6. That was the average, 5 or 6 of these transitions. And so over the space of hundreds of millions of years, there have only been 5 or 6 of these glacial, interglacial transitions, these ice age periods. And that's huge because planetary cycles, those types of ice ages, they cycle every 100,000 years or so, thousands of years, not millions of years. And so there's something going on with Mars having these huge long periods of the glacials and interglacials versus here on Earth, we only have ice ages that last 100,000 years or so. So what's going on? I don't know. And what's also interesting was that the rocks, because remember in that one model, we assumed that as rocks went down the glacier, they would erode, they would break down and get smaller. So you'd have bigger rocks up high, smaller rocks that went down through the glacier as they eroded down. They didn't see that in the Martian glaciers and the Martian debris. Rather, the rocks, they were the similar sizes, just scattered across the whole glacier in these bands, indicating that the rocks did not travel on the surface, rather they actually traveled inside of the Earth, inside of the glacier itself.
Yep, our suspicions were confirmed. It was an inside job.
So if we can figure out what is going on with Mars's climate, why it seems to be lasting 100 million years, and of course there's more data, there's more evidence to look at. There's more research that needs to go on to answer these questions. But if we can figure out what's going on with this climate, and if we can find evidence that the climate was ever warm or wet, look at these interglacial periods, the periods where the ice was melting, when there's more warmth, when there's more ice, like when there's more water, that could be the time when there is life. And what's amazing, this is the best part, what's great about ice is that it preserves things. Here on Earth, when we go to Antarctica or Greenland and get ice cores, we are recording gases that was in the atmosphere. We are recording ashes from volcanoes, ashes from coal plants. We have all of this wonderful data stored, locked in the ice. And now with these Martian glaciers, there is ice there. It's just covered in rocks. And if we can know where those are, drill down, we can get this valuable data that's been locked in the ice. Biosignatures may be locked in that ice. And if we can figure out that climate, figure out where in the ice we need to look, we might just find evidence of life on Mars. And what's more, we're trying to not just find evidence of life on Mars, we're trying to put life on Mars. We're trying to get humans to go up there. And humans, they need water. And if we can get the water from Mars, we can use that ice as a resource that's locked in these glaciers. We'll have to drill down, though. We'll have to get it. We need to understand how these glaciers look like, both on the surface and inside the glacier. We need to know where the rocks are so that when we're drilling, we know where we're going to get ice. We don't want to just be drilled through a bunch of rocks. We want to get to that ice. And so by mapping out these glaciers, understanding the climatic history, we can secure this ice as a potential resource for people. So there you go. Geomorphology, counting rocks. That's what's so great about science, is that these Earth systems are incredibly complex. But a lot of times the methods that we can use to solve these questions are relatively simple. This army of researchers essentially looked at pictures of Mars and counted where they saw rocks. But then by understanding these glacial processes, they were able to understand the climatic history of Mars. They were able to take that simple counting data, 1 rock, 2 rock, 3 rock, 4 rock, and I'm oversimplifying a little bit. But they're able just to count those rocks, map them out, and reveal this amazing story. So anybody can get involved in science. Anybody can get involved in research if you are excited about it. So go for it. And who knows, maybe you'll help find that biosignature somewhere on Mars. Well, that's it for today. So I'm going to leave you. Ciao.